maybe I can start with the bio of Joshua. So Joshua is a consultant at Deloitte within the business and algorithm team. He has practical experience in translating extensive academic learning from theory to practice in data science, behavioral economics, and finance. He has a strong interest in the synthesis of data analytics and human behavior, particularly in solving challenging, complex, and impactful problems, and is based in Australia. So Joshua, I think you have also two colleagues presenting with you, Abhishek and Petroula. Do you think they are joining, or do you want to go ahead with the presentation?
They're on the call now, looks like.
Yeah, hey, Frederick.
We're here.
Frederick, you might be on mute.
Yes, thank you. I can see you now. So I go ahead with the bio of Petroula. So she's an analytic professional with experience in delivering data-driven solution and decision-making with background and studies in applied mathematics and science. She's also working for Deloitte Australia. Her expertise in data and statistical analysis, as well as risk management, spans to a number of industries and concepts, including financial service, biomedical research, remediation, and supply chain. And then we have our third speaker right now, Abhishek, also working for Deloitte in Australia. He's also an analytic professional with a background in statistics and over 8 years of experience developing statistical and machine learning solutions to solve a range of problem statements for clients in financial service, retail, and telecom sector. He enjoys tackling complex business problems, developing innovative solutions to derive meaningful insight. So I can see you're sharing the screen already, so the floor is yours.
Abhi, do you mind changing from presenter mode just to the standard one, possible?
Is that coming through?
Yeah, I think that worked. Just make it full screen.
Yeah. Is it coming through now? Full screen?
But just in presenter mode.
I do have it on presenter mode, but I don't know if it's coming through to you. Or let me just share the desktop. Sorry about that. Is that working now?
Yeah.
Yeah.
Right. Okay. Hey everyone, welcome to our presentation. Thank you for joining us this afternoon. We're going to talk through 3 use cases for environmental analytics and discuss how each of them provides demonstrative value. And I'm going to start my segment off with a story. So my dad's South African, and when I was only a few weeks old, we left Sydney and went to live in Johannesburg. We lived there for about a year before coming back, and ever since then, we've been returning every 2 to 3 years for a holiday to visit family and friends. Sometimes we visit Cape Town as well. It's a beautiful city full of beaches and good food, enclosed by some spectacular mountains. But even when we do get the chance to visit Cape Town, the highlight of my trip is always the game reserve. The game reserve is essentially a large wildlife preserve. Most would know it as safari. We used to drive up from Johannesburg. It's about a 5-hour journey, and you really see the landscape shifting dramatically over that drive. You see the inner city full of tall buildings and coffee shops, and you get to the city outskirts, which really reflect the intense poverty of Johannesburg. And finally, you reach rural South Africa, which largely consists of farmlands and not much else. However, occasionally, the grasslands are punctuated by flourishes of industrialization. You see big shiny machines wheeling around and people all over the place with hard hats. It's such a stark contrast to the game reserve, which in my opinion, represents true coexistence between humans and nature. It's really an oasis. If you look at a map of the registered mines in South Africa, you can easily identify Kruger Park, the game reserve, as one of the few areas in South Africa with no approved mining zones. But that's legal mining. It can be devastating to the environment, but it's vital to the economy, and there is much debate about its place in South Africa. However, today I'm going to be talking about illegal mining. Illegal mining is not a contentious issue. It's unambiguously detrimental. Illegal miners in South Africa are called zama-zamas, which is a Zulu expression meaning those taking a chance. And sadly, there is justification for this saying. It is spectacularly dangerous, with hundreds of deaths over the past few years, numbers that are only increasing as the economy falters and people get more and more desperate. Additionally, it causes irreparable ecological damage. And finally, it costs the economy close to $1.4 billion a year by some estimates. So how do we resolve this issue? Well, it starts by building understanding. We do this through satellite image analytics. This provides us with 3 key insights. Firstly, the identification of illegal mines, the scale of those mines, their locations, and the speed with which they're expanding. Secondly, the algorithm allows us to perform retrospective analysis to evaluate the success, or lack thereof, of environmental protection laws. We can monitor the success of rewilding and cleanup of previously closed mining sites and ensure they're not resurrected as a final insight. Now let's discuss the solution itself. There are 3 main challenges to building an effective model for this problem. Firstly, and most importantly, illegal mines are never officially registered. By design, they are inherently and purposely hidden. This means that there is very little training data with which to build a sophisticated model. Secondly, protected regions are massive. In total, they cover around 15.5% of the world's landmass, more than 30 million square kilometers. That's about 3 times bigger than Europe. The sheer size of this area poses a computational challenge for advanced modeling approaches. Finally, cloud coverage can obscure areas temporarily. However, this problem can be fairly easily dealt with if a pre-processing algorithm is applied prior to the main model. So how does our solution work? We start by defining in-scope protected areas using an easily accessible, publicly available dataset. Then we divide this area into a number of zones, approximately 750 hectares each, like the one in the image to the bottom left of the screen. Then for each of these zones, we apply 2 algorithms. The first of which is a color segmentation algorithm. First, a range of tones associated with an illegal mine is specified. In this case, it would range from light tan to dark brown. The algorithm then segments the image according to whether a pixel falls into this range or not. It darkens and desaturates areas that are not directly irrelevant. This output then becomes the input to the contouring algorithm. This model looks for delineations or boundaries between light and dark and accordingly draws a distinction between them in the form of the red lines that you can see in the bottom right image. Lastly, the area of each region enclosed by these contours is calculated. This process is undertaken for each zone, and a list of suspect zones is then compiled, which would then be forwarded to an expert to advise on whether the zone does indeed reflect illegal mining. So taking this zone as an example, we can compare the contoured areas before and after an additional illegal mining expansion. First, it is important to note that we only really look at the top few areas. A threshold must be applied in order to filter out the noise and randomness. It is clear that the first two areas represent 1, the big mass center right of the image, and 2, the small island just to the left. Hence, when we consider the difference in areas before and after, we will only compare these two regions. It is evident that the larger mass has doubled in size, and we can further convert from pixels to actual land area with the understanding that each pixel approximately covers 5 square meters. The deterioration we can see represents an area of around 90 hectares, which is almost the size of Gardens by the Bay in Singapore. We can also easily compute the percentage of forestation lost in the latter image. In the after image, at least 28% of the forest has been destroyed. However, at this stage, it is important to note an important limitation of this analysis, i.e., we only see damage to the forest canopy. It is likely that the chemicals and machinery from the mining have polluted much more than the area visible from above. Therefore, the 28% is a rather conservative figure. So what do we learn from this analysis? First and foremost, we learned that complexity does not necessarily translate to performance. If we were to have built a highly sophisticated and complex model, such as a convolutional neural network, with such little training data, it is unlikely we would have achieved such strong performance. Secondly, and relatedly, flexibility is key. We need to be guided by the data. Don't jump into a piece of analysis with a preconceived idea of the model to be used. We need to be open-minded and listen to what the data is telling us. Lastly, an observation from me, the actuarial skill set is applicable in unpredictable settings. Certainly when I studied actuarial science, and I'm sure this applies to some of you, I never anticipated that the skill set would be applied in such an unconventional setting. Now I want to quickly touch on some wins from this modeling approach. Firstly, it's computationally cheap, which to some extent negates the challenge I raised earlier regarding the massiveness of protected land. Secondly, it's very intuitive and interpretable. It closely follows the approach a human might take when trying to find illegal mining from satellite imagery. It's also very easy to implement in a standard programming language, and it's remarkably accurate, even without training data. So what's next? There is scope for further improvement to the model. One of the advantages of the process I mentioned earlier is that you are, in effect, building a training data set when you refer a site for expert opinion. This may eventually be leveraged to create a semi-supervised model. And how might this type of analysis be used by government and conservation groups? Government could use this model to monitor illegal mining rather. The natural response from there would be to use the analysis to shut down operational mines. But I would suggest an alternative approach be conducted in tandem perhaps. Illegal mining is costly. You need to get the machinery to a remote part of the planet, clear out an area and hope that there are sufficient rewards to justify the means. If government made clear that they would stop these mines, i.e. they published and publicized that they were doing this sort of analysis, the value proposition for miners would diminish. This would save some of the vast amounts of money and resources it takes to shut down illegal mines. Finally, conservation and environmental protection groups could also use this model. It is a clear, visual, data-backed way to hold governments accountable for forestry mismanagement and to apply pressure to an issue that is often swept under the rug. Now hand it over to my colleague, Abhi.
Thanks, Josh. We'll move now from illegal mining to forest wetlands. So let's start by talking about how we define wetlands. It is quite hard to put an exact definition for wetlands, but they are generally thought to be like transitional zones between truly aquatic and terrestrial habitats. And why are we talking about them today, and why are they important? They actually play quite a crucial role in maintaining the balance in our environment. They are bursting with biodiversity, and they are essential for many amphibians and reptiles. Many birds as well depend on them for breeding and migration. They also help filter waste and purify the water flowing through them. They also help in combating climate change. They house close to 30% of the carbon found on land and reduce coastal erosion, as well as provide protection against floods. Globally, there's over 60 million people who are directly dependent on these wetlands for livelihood. Often, though, dams and river management activities which are done, might reduce water flow, which go into these wetlands, altering their ecology and thereby causing a decline in the flora and fauna that is found in these areas. We've lost close to 50% of the world's wetland over the last 100 years, and it is quite crucial that we sustainably manage these wetlands. That brings us to the topic of how we can use analytics to get more insight and understand the situation better and improving the situation. And it is a well-known fact that certain species within the habitat can be a good indicator for ecosystem health. And in case of wetlands, for example, population of certain frog species could be used to understand the effects or the impact some of these activities are having on the ecosystem there. So how do we go about, say, estimating population of these frogs, or how do we gather such information? One way is to deploy acoustic sensors within these wetlands, which can capture environmental sounds at regular intervals. These sensors need to be strategically placed so that we have a good coverage across the area, and also we need to capture these data over a period of time for us to make sense of them. Through this data, we can then develop acoustic detection models, which can help detect any calls from these frogs or certain bird species within these recordings. And this would be further useful for us in understanding if there's any patterns in or decline in the frog calls, essentially. We can further augment this data, this detection outcomes from the models with environmental data like rainfall or water flow data, temperature, so on. And we could conduct multi-factor analysis, which will help understand the impact that these factors are having on the native bird or frog species. I'll touch a bit more on some of those acoustic detection algorithms I talked on the previous slide. So there could be multiple approaches that you could take to tackle this problem. But one of the biggest challenges you might be facing is having the availability of classified data to train your models on, say, specific species. And in case of limited or no availability of such classified data, generally an unsupervised learning approach could be quite useful. We can do this first by segmenting the data that we have based on the habitat and geographic location of these recorders, processing the audio that is recorded, and preparing the data to be used for a cluster analysis down the line. So using parameters like the sampling rate of the audio or the rolling window that we want to use for the clustering, like for defining the sound bits. Those can be defined and played around with to further improve your cluster analysis. So following the pre-processing, we can then perform a KNN clustering algorithm or any other clustering approaches to segment these audio clips that we have and cluster together similar sounding sound clips. With help of, say, biological experts who can identify these species calls listening to some of these recordings, we can then use their expertise to leverage their expertise to listen to representative samples of each cluster and classify them into different species. And to further augment this cluster analysis as well, you could use the information which is classified along with the unidentified noises within the clusters and create synthetic data, which you could then use to further refine your clusters as well. And this synthetic data could also be useful in a way when you don't have classified data to understand the accuracy of your models as well. Now that brings me to the topic where we do have information or classified data available on certain species, in which case you could also leverage a lot of supervised learning techniques as well. Hidden Markov models are effective and wouldn't require a lot of training data. And in case you have a ton of training data available as well, you could use more advanced techniques like neural networks or XGBoost to build up these supervised learning models. And the general approach followed in these cases is to take the raw wave format that we have, transform that wave data into spectrograms, and extract certain septal coefficients, which might be useful in training a model with the classified information that we've got on these species. So there's a lot of work being done in this space using supervised learning as well. There's a lot of open data available in case someone wants to try their hands on it as well. I've just put in the link there for reference. All right, so detection algorithms that we talked about is one aspect to it, but there is a lot more beyond the detection models as well to actually make sense of the outcomes and actually generating meaningful insights that we could act on. So we start by using the detection model data and creating metrics which are computed on these detection outcomes. Like say, for example, species activities index, where we look at frequency of these detections over time, species evenness index, where how often or those detections are happening across different locations. And also species diversity index, like what are the different set of species that are identified in certain locations. Such metrics can help us cut through the noise and enable a better understanding of the overall population trends. Using environmental data such as season, water levels, temperature, rainfall, time of day, to augment this detection data further, we can then use these metrics across these factors to understand the impact of these factors on different species. The analysis can be helpful, for environmentalists to understand how reducing, say, the water flow from dams can impact such ecosystems downstream, and it would provide us an ability to understand and manage the impact in a holistic manner and determine the appropriate optimized strategies for us to preserve such ecosystems. With that, I'll pass on to Petroula.
Thank you, Abhi. So from wetlands to natural disasters, I would like to start by just recalling some climate events from the past that led to a significant amount of damage in general, but also focus on the property-related damage that was caused. So just to begin with, the cyclone Debbie in 2017 in Australia resulted in more than 72,000 insurance levy claims and more than 1 billion paid in insurance claims as well. And then moving on to Sydney hailstorm back in 1999, which left more than 24,000 houses damaged and a total cost of more than 2 billion. Of course, there are other significant events that we will remember, such as the Australian bushfires that started last year in November, as well as other severe weather conditions that have also been observed around the world since then and causing damage to properties. So such severe weather conditions are occurring around the world. And in fact, there are studies showing that the frequency and the severity of these extreme climate events follow an increasing trend. In such scenarios, there is need for insurance companies to process claims as soon as possible in order to give relief to impacted and distressed customers. The question is how we can use data and analytics to respond faster to customers and at the same time streamline the claims process. So the answer begins with data enrichment and data collections, which can be processed to derive useful insights. And of course, there always has to be a data source. And in this situation, we study how data deriving from satellite imagery can be used to identify homes that are damaged from natural disasters, and what are some other benefits and use cases of such data collection. So I'm just going to talk through three main benefits that can be derived through embracing satellite or aerial imagery in the insurance claims process, and especially I'm going to talk through property damage related claims. So first, to begin with, is the early detection of the damage. So before and after event imagery can be derived from the satellite and be used to detect changes and thus damages of a property. Second in the role is the claims validation process. So details regarding the cause and the date of the damage can also be derived from processing satellite images, and moreover details with regards the area of the damage can indicate the level of severity as well. So last but not least, other property characteristics can be collected, such as like different property features, and if this is combined with metrics such as the frequency of the climate events in particular areas, can enhance the predictive risk modeling and assist also in decision making. So just to explain a little bit of the importance of the above, I'm just going to talk through the specific example of the hailstorm. So knowing that a particular area has been affected by a natural disaster, imagery from before and after can be used to detect whether a property has been affected. So you can see in the images that after the storm, damaged roof have a blue tarpaulin cover, and this can enable the damage detection, but also can help in estimating the number of claims that are about to be submitted in the next hours or days, and that can help with planning. But it's not only about the early detection of the damage. Data can be collected from satellite to streamline the claim process even further. So just to begin with, a very useful scenario would be to answer questions. So for example, in the case where damage has been observed, but the cause and the date of the damage are unknown, before and after image that can be derived from a satellite can throw some light in this case. In addition to this, satellite imagery can also help to combat fraud. So can help in verifying the real cause of the damage and whether it should be covered or not. Next, I would like to say that it can also help with targeted assessor deployment. So data can be used to indicate the severity of the damage. So for example, like the blue cover area that we saw in the previous picture from the hailstorm scenario can work as an indicator of the level of severity. So having this in mind, on-site visits can be more targeted. And for example, the most experienced assessors can investigate the most complicated claims. Last but not least, I would like to mention how satellite imagery can streamline the decision making. So already existing property data can be enriched after processing satellite images. So details about property condition, or for example, already existing damage or other features such as roof materials can be derived and incorporated into predictive risk modeling and underwriting decisions as well. So the main advantage here would be first would be the faster process of claims. So with having with investigations that they go faster, assessing claims and helping validating the repair estimate faster, the distressed customer can receive response much quicker. So at this stage, I would like to say that there are many different algorithms and analytical techniques that can be applied in streamlining this process, and that's very much dependent on the use case. So, however, I would like to mention two main challenges that, regardless of the use case. So first is potential misclassification, and especially for the scenario with the hailstone with the blue roof covers, there is a chance that some other objects of similar color or similar shape around the area, such as blue cars or pools, can lead to classifying the property as damaged. However, this can still be a really good estimate about the damaged houses around the area after a climate event. And second, and most important, there is an ethical question whether property data collection should be allowed and under which circumstances. And I'm particularly talking about, I'm referring about data gathering data about property features and conditions, with main goal taking data-driven decisions. And some cases the house owner may not willing to give the consent for this. So finally, I would like to close this presentation by saying in general that the environment often defies expectations and belies understanding, but developing a appreciation of the environment is becoming increasingly important. So as we discussed, our interaction with the natural world, always complex and often extraordinarily impactful. So we really hope that this presentation has illuminated the importance of understanding the environment and the ways in which we might seek to engage with analytically. Thank you very much for joining us.
Thank you. Quite a refreshing presentation with some concrete application of satellite image. Let me check if we have some question online. No, we don't have question. I just had a pragmatic question, especially the presentation you just did, Petroula. Is it really easy to access? Is it open source, all this satellite image?
Yes, there are some open sources, but so really depends on the use case. So for example, in scenarios where we need historical data and historical images, just for example, when I mentioned to verify or identify the date and the cause of the damage, that might be a little bit more challenging, but yes, there are some open sources.
And then I have the next question. Especially if you're, I mean, in this case of assessing if some insured were hit by a storm or any natural catastrophe, is it quite easy to, like to map the satellite with postal code and address to see which insured is covered or not, or is it quite challenging?
Yes, satellite can link the property to the address.
Okay, and so it can have a real pragmatic kind of claim assessment if now you're able to map with the address quite easily. Yes. Yep. Okay. So I give, since we have 4 more minutes, I give some more time for question to pop up. Unless you want to ask questions to each other. Okay. So I think we can close this presentation. So thank you very much, Joshua, Abhishek, and Petroula. It starts to be late in Australia. I think 6 something. So thanks for doing the presentation a bit late in the